Thank you very much for this conference. I have to admit, I wasn't even sure a couple of days ago that it was going to happen. Very happy that it happens. It's been a long time I haven't been here in CIRM. That's very nice. I'm going to talk to you about the work with Nicolas Curien, Luis Fredes, and Avelio Sepulveda. So the point is to look at the scaling limit of a model of maps without using the classical approach, which is, well, usually you have a model of map, you have a nice bijection, you use the bijection, and you work with the bijection. And here I don't want to use the bijection because there is a bijection, but the bijection is not very easy to work with. So the point is to use another model that is quite close and for which I already have the result. That's the point. I'm going to define, I know Marie already did it, but let me just do it again very quickly. I'm going to focus on plane maps. So once again, it's a graph embedded in the sphere. You have vertices, you have edges linking the vertices, and you have faces. And the condition is that the graph has to be connected. And also, for technical reasons, we often consider rooted maps, which means that there are many conventions, but I can say here that one corner is. So here is a famous example of plane map. I had to remove some parts because I wanted it to be connected. Sorry for people on Zoom. So it's in a couple of years it's going to look maybe. Okay. And the topology I use is the Gromov-Hausdorff topology. Very common in this setting. So the idea is that when you want to compare two sets like this, the first step is to try to fit them as well as possible, and then use the Hausdorff. Okay. So if you want to be a bit more formal, the Gromov-Hausdorff distance between these two compact sets. Here, you take the infimum of the Hausdorff distance between the embeddings phi of x and phi prime of x prime, where I take the infimum over all possible embeddings into the same common metric space Z. So the most famous result in the area is the following one, the definition of the Brownian sphere. It says that if you take a map, so here my map is M, and the metric I put on the map is the graph metric prescaled. So here A times M, it means that all the edges have length A. Another way to say it is that I look at the graph metric, so the distance between two vertices is the number of edges you have to cross to go from one vertex to the other one, and you multiply this length by A. So the result is that if you take a uniform plane quadrangulation with n faces, so it means that you have n faces, and all the faces have degree 4, so there are 4 corners. So if you take this model, then up to this scaling factor, you have convergence to metric space, a limiting metric space in the topology I described before, and we call it the Brownian. We used to call it the Brownian map, but nowadays most people say Brownian. Some people also still say Brownian map. The same, it's the same thing. It's not a critique. Do as you want. It's the same guy. Maybe to be a bit more precise, this theorem says that you can embed all your spaces, all these guys, into the same metric space in such a way that in this metric space you have convergence for the Hausdorff. Yes, this is not a mistake. Well, yes, most of you already know that, but it's really a theorem that was shown by two different approaches, by Le Gall and by Mirmont in 2000. That's yes, deterministic. And this is a picture. This is a uniform plane quadrangulation with 50,000 faces. Looks like this. Very nice sphere. Let me talk about some earlier results. Complete the presentation. First of all, in 2004, Chassin and Schaeffer observed that the scaling factor was n to the 1/4. And they showed the scaling limit of some functionals, typically the diameter, the radius, and the profile. The radius is the distance between one fixed point and the max of the distance between one fixed point and all the other points. And the profile is the distribution of all the vertices at given distance from this fixed point. And then in 2006, Marker and Mokadem introduced the notion of the Brownian sphere, the time they called it Brownian map once again, and they showed the convergence in some sense with this guy. And then in 2007, Jean-François showed that the convergence in this setting of Gromov-Hausdorff, but up to extraction. So he showed that the sequence of quadrangulation was relatively compact, which means that you can extract subsequences along which you have. And he also showed that the limit had the topology of the sphere. No, sorry. That all the possible limits had the same topology, and that the Hausdorff dimension was always 4. And he also showed with Paulin that the topology was that of the sphere. That's why I said the previous picture it was a nice sphere. Well, Gregory also showed the same result by another approach, really kind of a backward approach of what Jean-François and Paulin did. And also in 2008, Boutier and Guiter look at what we call the 3-point function, which is the limiting joint distribution between 3 points. So you take 3 points in your random quadrangulation, and you look at the limit. Okay. Next, I want to recap some results about universality. A very nice property of the Brownian sphere is that it is universal in the sense that it is the scaling limit of somehow all natural models of maps you can think about. And if you don't, if you haven't seen that before, you can think of the Brownian motion. If you take a random walk, you take a reasonable random walk, it will always converge to the same object, the Brownian motion. So here it's the same idea, or the same kind of result. Okay, you take a natural model of maps, it will converge to this Brownian sphere. So I have many examples. So first of all, Le Gall also considered not just quadrangulations, but also p-angulations. So it means that all the faces have degree p for these numbers, so either even or 3. And also for maps with a Boltzmann distribution. And then with this approach, we had many more generalizations. For instance, quadrangulation without vertices of degree 1. Just remove the vertices of degree 1, then you take a uniform map like this, then it also converges to the same object. And other examples For instance, simple triangulation or simple quadrangulation. They are same kind of constraint as this one. Here you forbid the multiple vertices, meaning that you cannot have the multiple edges. Sorry, you cannot have two edges linking the same vertex. And other results. Okay, I'm not going. As the list becomes longer, we have. Let's talk now about maps of the disk. So far, I was working on the sphere. Now I want to look at quadrangulations on the disk. So the definition is the following one. I take what I call a plane quadrangulation with a boundary. So it's still a plane map, but all the faces have degree 4 except one. And usually it's the root face. Here I put an arrow instead of a corner as before, but it shows one of corner of the map. So one face here, the white one, the infinite one, the unbounded one, doesn't have degree 4. And I insist on the fact that the boundary is not necessarily simple, which means that when you go around the boundary, maybe you can meet some vertices twice, or even more than twice. So here, for instance, at this vertex there, when I go around, I meet it once. And so this is completely allowed. And so for this model, we have many results. We know that if you take a uniform quadrangulation, so here I have n, the number of faces, and the boundary length t. The number of faces, I will call that the area, and the number of edges on the boundary, I will call that perimeter. So if you take the perimeter that behaves like a number times root 2n, then you have convergence towards a random metric space. It looks like the Brownian sphere, but it's now a Brownian disk. It has the topology of the disk, and the Hausdorff dimension is also known. It's the same as for the Brownian map 4, but we can also look at the boundary. Here the boundary has dimension 2. Okay, so this is a result with Grégory Mirmont. We can also, so this is a computer simulation. You have 14,000 faces and a boundary of length 1,000. So the boundary is the red there. So if you look there, you can see something that looks like the Brownian sphere. But if you look around the boundary, it's a bit different. The colors are here. There is a hole. You can see inside the structure. That's why it's not the same. Sometimes people don't understand what we see. So here we see something that like this. So now what happens when the boundary, the length of the boundary is not of order root 2n? If it's smaller than root 2n, it's actually negligible with root 2n. Then we have convergence to the Brownian sphere. The boundary collapses into a point to see the Brownian sphere. And if the boundary is too large with respect to root 2n, then you have to, well, you only see the boundary, so you actually have to rescale your space a bit more. So instead of rescaling by n to the minus 1/4, you rescale by the boundary. This is the length of the boundary to the minus 1/2, and you have convergence to a tree. The Brownian CRT, which is the universal scaling limit for models of trees. So if you want, as you rescale more than n to the 1/4, n to the minus 1/4, you don't see the faces anymore. You just see the boundary. And in the end, you have a scaling limit of your structure, which is, at this scale, it's a tree, because you don't really see the faces. So it's the same scaling limit as for the tree. You have, I didn't put it on the slide, but Cyril Marzouk has some more general results than that. He can actually generalize this to many other models of maps. As I said for the sphere, the result I said for the sphere, I cited for the sphere also works in this. And furthermore, Boutier and Guiter already, in another approach, already observed that these two regimes were appeared in the context of the two-point function, so the distance between two vertices in the map. Okay. So here's a computer simulation. You can see that when the boundary is large with respect to the number of faces, square root of the number of faces, then you only see the boundary. That's why I'm saying that always almost. Okay. We also have many results of universality in this case. For instance, this is a result with Gregory. If you take, instead of taking a quadrangulation with a boundary, you take a P angulation with a boundary, where P is I didn't write, where P is an even number, then you also have convergence to the same Brownian disk. Only the scaling factor is the scaling factor always. The scaling factor is the thing that depends on the model. Also, if you take a uniform bipartite map with a given area and perimeter, where the parameter is also always in the regime, the square root of n, then you have convergence to the Brownian. I didn't say what bipartite is, but the technicality saying that all the faces have to be of even degree. And actually removing this this constraint is quite annoying. And a paper that I cited but didn't speak about was for the case of P angulation where P. Oh yes. Sorry, I was mistaken. So it's 2P and not. So P here is not even 2P's. Yes, on a paper cited by Luigi Ruberi and Marie Albank, they looked at P angulations for odd P, and that takes a lot of work to consider odd P's instead of even. Okay. We also have more universality results for Boltzmann maps, but more complicated to present them. I'm not going to do that. And now the result I want to focus today is the one about plane quadrangulation with a simple boundary. So now the model is that you take a quadrangulation before with a boundary, but now you ask that the boundary be simple. It means that when once again when you go around the boundary, now you don't see you see all the vertices, you see them only once. Another way to say it is that all the edges on the boundary, they have one side incident to the external face and one side incident to an internal face. You don't have an edge that sees the external face for both So the result is almost the same. You take a uniform, this here, I put a tilde on top. So here it's still the number of faces and p, the length of the boundary. So if the length of the boundary is in the regime root to n, we still have convergence to the Brownian disk. The difference is that here we have a 3L here. Remember that if we remove the tilde here, the result we had with Gregory was that this converges to the Brownian disk of perimeter L. With the tilde, it's perimeter 3L. This is a joint result with Nicolas Curien, Louis Fortes, Navalio, etc. So this is the result I want to focus on now. So how do we show this result without using the usual road, but with by comparison with a model I already know results about. First of all, I will define the core of my map. So here I have a quadrangulation with a boundary, a generic boundary. And I want to define the core of this map. If you look at all the edges on the boundary, so you have edges that are incident to an interior face, and edges like this one that are incident twice to the external face. If you remove all these edges, the latter ones, so the ones that see the external face from both sides, then you have a collection of components. And the thing is, if I have a pointed map, let's add the point here. If the point, so the point is a vertex. If the marked vertex falls into the largest component, then I take the largest component. And if it falls in a small component, then I take nothing. Take a symmetry point. Okay. So the idea is that most likely the point will be in the large component. Then you just take the component where the point is. And if it falls in the small component, it's not very important. We know some asymptotics about this. So if you take a, here I don't have a tilde, so it's a quadrangulation with n faces and boundary length t, but the boundary is not simple. Then the probability and the perimeter, so the boundary length, I ask it to be in the regime root to n. The probability that the core is equal to this symmetry point goes to 0. It means that most likely the core will be well defined, will be really a map, not a symmetry point. And the area and perimeter of the core are known to be, so the perimeter, or the area is of order n, and the perimeter is roughly a third of the original perimeter. So we have this convergence result. It means that, once again, if you take a big map, then and you take it pointed, then the point most likely will fall into the largest component. And this largest component roughly has almost all the faces, or the number of faces that are not in there is negligible with respect to n. And the perimeter is roughly a third of the original. So it means that, well, some observations. So conditionally, given the area of the core and perimeter of the core, then the core is a uniform quadrangulation with a simple boundary, but having this area and perimeter. So these are random numbers. And also, it's not very complicated to see that we know that this object, so this Qn ln point is a uniform quadrangulation with n faces and a boundary of length 6 ln, and then a uniform point. This doesn't change anything. We know that this converges to the Brownian disk of parameter 3L. This is the result, the result with Gregory. And if I take the core of this, as the core actually almost has all the faces, it's not very complicated to see that the small components on the boundary, there are we don't see them in the scale n to the 1/4, and the core actually also converges to the same object. Also remember that the object here is a disk, topologically a disk, whereas here the boundary was not simple. So it means that the small components on the boundary, they disappear at the limit. Maybe that's easier to understand the result when you with this observation. Yes. It's the same. Yeah, you take the map, you remove the small components, then you have the same limit. So yes, it is a joint conversion. Well, actually, we will not need it here, but that. So what I'm saying is that if I take now my simple quadrangulation, remember the tilde means simple boundary, with a fixed perimeter and area, then it's roughly the same as this one, because an is roughly n and tn is roughly 2ln, and this one has the same distribution as the core of a quadrangulation with a generic boundary. So the question is, knowing the convergence of this one, how can I get convergence of this one? So we need to actually find a conditional convergence when an and tn are exactly this and not roughly this. The idea to do that is to prove that large parts of these two guys are arbitrarily small in total variation. We'll explain this. What I mean by large parts, to do this, I use what we call restrictions. And it's defined like this. So you take a quadrangulation with a simple boundary. So now I have my two objects. They all have simple boundaries, because now I compare. I don't care about this one anymore. I really care about this one, which has a simple boundary, and I know that it converges, and this one, which has a simple boundary, and I want to show that this also converges to the same guy. So I have a quadrangulation with a simple boundary and a marked vertex here. First of all, I number the vertices on the boundary like this, starting with the roots. Then I go in this direction, and I focus on the one here that I call T here, the 8th one on this example. It's the one that lies at a third, not on the boundary of this guy, because this guy, there is no n here, but a third of the boundary that I want this guy to have. Okay, I don't know if I'm clear, but 2ln here, it's not the length of the boundary of this one. It's the length of the boundary I want my map to have. Okay? I will, of course, I will use the restriction when this map is my Qn something. So it will have roughly length this, but this number does not depend on the map. That's what I'm saying here. And I look at the part of the boundary of length epsilon times 2ln. And then I grow balls from this vertex here. So what I mean by that is, first of all, I take all the vertices that are at distance 0 from this one. So it's only the yellow one. And then I look at all the faces that touch it. And I will call it the ball of radius 1. Then I add all the vertices that are at distance 1 from this guy, the 3 orange one. And I take all the faces that touch it. And so on, at distance 2, all the faces that touch it. And I stop when my ball hits the blue part here. I call V minus the point where the ball touches the blue part. Well, of course, it could touch it at multiple points. Well, in this case, I take the closest to my T here. That's just a technicality. And then I call V plus the first point after T of the ball. Well, of course, it's possible that the ball does not touch on the other side, but in this case, this is something that will happen with a negligible probability. So here again, I will remove this. Once I have done that, I look at all the complements of the ball, and I add all of them to my ball, except the one that contains something we usually call the hull, for some reason, of the ball. Okay. Yes. It's the first point on the boundary afterwards. So between T and the root. It's not, well. Yes. No. It has length epsilon. Okay. So you have two. So you have one component that contains T, and all the other ones you add them to your thing, and that is what I call the restriction. And the complement of the restriction is the leftover. Like complement in terms of face. So my point is that this restriction here will be a large part of the map. And this is the things I will compare in my two different models. So let me give you the proof and the general idea that actually can work for any model you want, provided you have some technical estimates. If you have your technical estimate, you can do some. You can use this approach. So that's why I use new letters for my models, because it does not really matter that I'm talking about these kind of map. So I want to study a model that I call X in red, and I know a model that I call Y in green. And this is the scaling factor. So I already know that this green model converges to something. And my aim is to show the same results with an X instead of Y. So I'm saying that provided that I have these two technical estimates, then I will have the result. So the technical estimates are the following one. So first of all, if I take the restriction of my two models, they are close, in the sense that the total variation distance between these two guys tend to 0. And furthermore, the part I removed, the leftover, the component that contained T, is small, in the sense that if I look at Yn and the restriction of Yn, the once rescaled, the Gromov-Hausdorff distance between these two guys, the probability that it is larger than some delta, will tend to 0 as n and tend to 0 and to n to infinity and exactly the same with the two models. So if I have these two estimates, well, these two, then I can transfer the convergence of yn to that of xn. I actually included the proof in order to convince you that it's very, very short and very easy. Let me quickly tell it. So first of all, you assume that you have convergence almost surely instead of in distribution with the Sorokod's embedding theorem. And you take a uniformly continuous function f. So you want to bound this. So either an is close to x, anx ax is close to y or not. So if an is close to y, then this is small. And otherwise, if ax is far from y, then you can bound this by using the bound on f, and you get this inequality here. So what you want to focus on is the probability that the distance from y to ax is large. So you introduce ay. So either I say ay instead of anyn. If the distance between these two guys is large, it means that either one of the two is far from anyn. And for this one, it's easy because you know that this guy converges to that one. So this will, you can make it small. And for the other one, you will use the technical estimate. So either ay, either the restriction is the same or it's not the same. So here the restriction is not the same. And if the restriction is the same, if the distance between these two is larger than the 2 delta, it means that one of them is at least at distance delta from the restriction, which is the same. So either ay is far from the restriction or ax is far from the restriction. And then you can, using the technical estimates, you see that these two terms, so the first line and the second line, are small. The first estimate exactly tells you that these guys are small. And the second estimate tells you that with a large probability, the restrictions are the same. So it means that the probability that they are not the same is arbitrary. OK. So we have two things to show. First, we have to, well, I start with the one with this one. We have to see that the restriction of my two models is small. To do that, it's actually just using counting arguments. Because what is the probability that my restriction is equal to a given R? I want my map to, I want the restriction of my map to be this R. So the question is, what should I add there to have this restriction in the end? So it's actually just counting the number of maps I can add here. So it's just a number of quadrangulation with the right parameters. And these numbers, the number of quadrangulation with a simple boundary with given parameter, has been computed by Boutier and Guiter. So we have explicit formulas. And we know that in probability, my parameters are going to be for the Fick, this one was with the Fick parameters, and this one, it has random parameters, but the random parameters, they are close in probability to the one that I have picked. So using this, I can easily enough show this here, but okay, right. So now for the other result. So here I will actually use a bijective method, but for my other model, not for the model I study, for the other model. My point is, once again, to have the results of convergence for the model I want to study without using the bijective encodings of this model. But I am allowed to use the bijective encoding of the other model. So my goal is to show that I recall the notation. I called yn, green yn, the core of my map with a generic boundary. No tilde here. So I have n faces and a boundary length of ln, and the boundary is not simple in this model. So my point is to show that the distance between my model and its restriction is small. So to do this, I use the classical encoding. So let me recall it. A quadrangulation with a boundary will be encoded by a label forest. If you don't know what it is, so it's a forest, so it means that you have trees. Here I have the first tree. So it's drawn like this, but it is a mathematical tree. And you have 2, 3, 4, 5, 6 trees here. And on the vertices of your trees, you have labels that should satisfy some constraints. There should be some, whenever they are close, whenever they are neighbors, the labels should not vary too much. I'm not going to give you all the details, but it's not the same condition on the green edges and the burgundy edges, but you have a constant here. And the bijection goes like this. You first add, okay, oh, I didn't say also that all the labels are positive, and the smallest one is 1. You add a point, a vertex with the label 0 in there, and then you go around your forest, and you add a new edge between each corner, the corner you are visiting. You link the corner you are visiting to the next one with a smaller label. So here you start at corner 3. So you will look at the next 2 there. Now you are there. You look at the next 1, 3, 2, 1. And you keep going. Now you are there. So you look at the next 2 there. You are at 2. You look at the next one there. When you are at 1, the only corner with label 0 is the one is the vertex added. So you link there. And you keep going. You are here at the corner label 2. You look for 1, this one, and so on. You do that for the whole tree, then the next tree, and so on. And when you are finished, you remove all the initial edges, and you get a quadrangulation with a boundary. Of course, you can use this. You could use this bijection and ask yourself what is the constraint on the labels so that the result has a simple boundary. But the constraint is very complicated to work. Important facts about this bijection. So it's a bijection between the labeled forest having n edges and L trees, and quadrangulations having n internal faces, so area n, and perimeter 2L. There is a technical condition in green that you don't need to read if you don't know this. And very, very important fact is that the labels on the forest, they give the distance to the distinguished point. We'll need that. So this encoded passes to the limit, like this. Well, there is a shift because I asked the labels to be positive. That's not very important. After scaling, the labels on the boundary, they converge to a Brownian bridge that I will denote by B. and the labels and the trees with their labels of the forest, they all converge to Brownian trees with Brownian labels. Well, so if you don't know what this means, just imagine a continuous tree with continuous labels that satisfy, that behave like Brownian motion. I know it's a bit blurry, but probably other people will talk about this construction in more detail later in the week. And also a very important fact is that the boundary of the core is very well spread inside the map. So it means that if you go, maybe draw a picture. If you look at, okay, I don't know how you did it, Mary, but sure. One second. Okay, so you have the core and small component. And if you go around the boundary like this, and you look at the times at which you are on the boundary of the core, well, they are roughly well spread. So here, if this point, let's say the root there. So this is, if I look at the boundary of the core, and so on, okay? And if I go, maybe another color. If I go there, here I go there, so on. There I have JK. What I'm saying is that JK is roughly 3K. Okay, so once every 3 vertices, I'm on the boundary of the, more precisely, this result. So remember that I will look at a map with a boundary of length 6ln. So on there I have 6ln vertices, and the position of the case vertex of the core is roughly 3 times more on the boundary of the initial. Okay, so here the same picture, but nicer maybe. In yellow you have the core, and there you have the dangling part on the boundary. There I don't have the forest, just the map and its core. And I want to look at the restriction. So to get the restriction, remember that I wanted to aim at this point at distance 2ln/3 on the boundary. So it's indexed by j 2ln/3. Means that when I go like this, when I go around, I arrive there at time j 2ln/3. And I want a part of length epsilon times 2ln. And I stop whenever I hit, so I will grow balls, and I stop whenever I hit this blue part here. So here, I hit the blue part there. So it means that this point here is the closest to my distinguished point. And if you remember that the labels on the vertices give the distance to the distinguished point, it means that this one is the one with the smallest label on the blue part. That would be important. And this one here is the first one afterwards with the same label as this one. Of course, I cheat a bit because I have faces, so I have plus or minus 1. But let's forget about this. So roughly all the labels along this part, along this boundary, this is part of the boundary of the ball. So they are all at distance, at the same distance from the distinguished up to plus or minus. Okay. And then now I imagine that I have my forest drawn inside this map, and I look at the what we usually call a simple geodesic. So it means that starting from there, you have some label, say L, and you look at, you will link this point to the next one with label N-1, and then you can keep going from this point with label N-1, you look for the next one with label N-2, and so on. When you do that, you draw something that actually will be a geodesic because the labels are L, L-1, L-2, and so on until the point. And you know that this is at distance exactly L, so you have a path of length exactly L, so it is a geodesic. We call it simple geodesic. And you also do the same starting from this part here. And what is important is that the orange thing I want to bound, so remember that my point is to bound the size of this guy, the diameter of this guy. Well, this guy is actually trapped between these two geodesics. So it means that it is actually encoded only by the part of the forest between these 2 points. So if I only keep the trees that are there between this point and this point, I will have all this. I will encode all this part, a bit more, of course, but at least all this. So if I take a point inside this orange thing, and I draw also the geodesic as before, then I will have to cross the boundary, and I will have to meet at some point one of these two geodesics. It means that the distance between the first point, the first black point here, and the second black point is smaller than the labels, the difference between the labels of these two guys. So if I pass to the limit, my point will end at distance at 1/3, because my bridge was on 0, 1. This point is at 1/3. And what is T minus is this point. So as I said, it's the point with smaller label on the blue part. So if actually in the limit, it will be the argmin of my Brownian bridge. The labels on the boundary here at the limit make up my Brownian bridge B. So this is the argmin of my bridge. And this here is the first point, the first time after a third, where the value of the bridge is the same as at this point. And the distance between y and the restriction will actually be bounded by the max of the labels minus the mean of the labels in the trees that are between T minus and T plus, because, as I said, the trees between T minus and T plus, they encode at least all the orange parts. So this gives me a bound. And so it's just a matter of seeing that you have a Brownian bridge. So it's just a computation. You just see it on the Brownian motion, and you see that it's going to be arbitrary, right? And let me just, you have 2 minutes to finish, or okay? So just to finish, I want also the same result, but with my model under study. So the quadrangulation with a simple boundary. And I don't want to use once again, to use the bijection. So here I use actually a resampling argument that roughly goes as follows. I had my notion of restriction. I define another notion of restriction going backwards. So instead of going 1/3 in this direction, maybe you wondered why I put 1/3 instead of a half. That's for this. Just for this, the only reason. You go 1/3 in the other direction. So you have two restrictions. This, the first one, and the second one with the prime. And the question is, why is x close to its restriction? Well, we use the fact that we know that if you take a restriction, the things are close. That was my first technical result. And then, so I go back to my model y. I know that the restriction I know that for y, it is close to the restriction. So for y, I can take my first restriction. And now this is also a restriction, and I know that when I have a restriction, I can put x or y. So it means that if I remove the green part, having or not the orange part doesn't change much. So even if I had the green part, removing or not the orange part doesn't change. Of course, it's a bit with the hands, but that's roughly the idea. OK. Thank you.